In this lecture, we're going to cover section 1.4, complex numbers. So the first slide begins with definition of a complex number and imaginary numbers. So some of you might remember that we can work with what's called an imaginary unit. We call it I, and it's defined as the square root of -1. Because remember, when we take the square root of a value, that value can't be negative, right? Because there's nothing we could square that's going to result in a negative number. So the square root of a negative number is imaginary. So the imaginary unit I is defined as the square root of -1. And if we were to square I, which would be the square root of -1 times the square root of -1, it would be equal to -1. So I squared is equal to -1. Now we can write an imaginary number. Well, let me back up for a minute. Let's look at this definition right here. So it says the set of all numbers in the form a plus bi with real numbers a and b and I, the imaginary unit, is called the set of complex numbers. So think of a complex number as it has a real part and an imaginary part. So the A and the B are real numbers. And remember, I is the imaginary unit. So typically, the standard form of a complex number is A plus BI. So we write the real part and then the imaginary part, and that's standard form. So for example, 2 plus 3i is a complex number. 2 is the real part, 3 times I is the imaginary part. Now, we can add and subtract complex numbers as we would any real numbers. So the form of a complex number, a plus bi, is just like a binomial, a plus bx. To add, subtract, multiply, and divide complex numbers, we use the same methods that we would use for binomials. So let's look first at adding and subtracting complex numbers. So if we wanted to add, like in number 1, a plus bi plus c plus di, we would add the real parts, a plus c, and then we would add the imaginary parts, bi plus di. And really, we're adding b plus d. And then that'll be your coefficient, the real part of, the real number b on that imaginary part. So in words, this says that you add complex numbers by adding their real parts, adding their imaginary parts, and then expressing the sum as a complex number. Very similar for subtraction. Very important, though, that we keep the second complex number in parentheses when we subtract, because remember, we have to distribute the negative. Okay? And we're going to practice. So look at example 1. It says perform the indicated operation and write the result in standard form, which is, let's just put up here to remind ourselves, a plus bi. So what if in A, I want to take 5 minus 2i and I want to add 3 plus 3i? So this is 5 minus 2i plus 3 plus 3i. So add the real parts. So we're going to have 5 plus 3, which is going to be 8. And then now we can add the imaginary part. So negative 2i combined with a positive 3i is going to be a positive 1i, or just I. We don't really need to write the 1, right? 8 plus I is the same thing as 8 plus 1i. And that would be your standard form. Very similar when we subtract, but like I said, don't forget we have to distribute that negative. So in B, if I want to take 2 plus 6i and subtract 12 minus I, we're going to have 2 plus 6i. Now distribute the negative, so minus 12, and then we have a negative I, so that's going to be plus I. And now we can combine like terms. So let's add the real parts. So 2 combined with a negative 12 is going to be negative 10. And then we have a 6i combined with a 1i, and that's going to be a positive 7i. So we have negative 10 plus 7i, and that's how we write it in standard form. Now we want to find the product. So in example 2, we're going to multiply. And we use the same rules as if we were multiplying polynomials. So look at A. We have 7i times 2 minus 9i. So we're going to take 7i times 2, which is going to be 14i. And then 7i times a negative 9i. So that's going to be a minus 7 times 9 is 63. I times I is I squared. Now, just a reminder, I squared is equal to negative 1. So wherever we see an I squared, we can evaluate it as negative 1. So here we have 14i minus 63 times negative 1. So we're going to have 14i, and then a negative 63 times a negative 1 is going to be positive 63. And if we write it in standard form, it's going to be 63 plus 14i. Now let's look at B. So now we're multiplying complex numbers again, right? But both have a real and an imaginary part. So we're going to distribute as we would if we were multiplying a binomial times a binomial. So we're going to have 5 times 6, which is 30. And then we're going to have 5 times negative 7i, which is going to be a negative 35i. Let me make this a little bit bigger. Now we have 4i times 6, which is going to be a positive 24i. And then we have a 4i times a negative 7i, which is going to be negative 28i squared. And let's combine like terms and simplify, right? So we have a 30. Now let's combine the two middle terms, right? The negative 35i with the positive 24i. So that's going to give us negative 11i. And then minus 28, but remember I squared is equal to negative 1. So 28 times negative 1. So we're going to have 30 minus 11i. Negative 28 times negative 1 is going to be positive 28. And now I can combine the 30 and the positive 28. That's going to give me 58. And then minus the imaginary part, which is 11i. So 58 minus 11i. We'll do one more. Look at part C. Same thing, distributive property. 3 times 2 is 6. 3 times negative 3i is negative 9i. 5i times 2 is going to be positive 10i. And then 5i times negative 3i is going to be negative 15i squared. So we're going to have 6. Now combine the negative 9i and the positive 10i, which is going to be positive 1i. And then minus 15 times negative 1, right? Because I squared is equal to negative 1. So we're going to have 6 plus I plus 15. And we could combine the 6 and the 15. And that's going to give us 21. And then plus I. So my standard form after I multiply out and combine is going to be 21 plus I. So example 1, we're really just to go over how we add, subtract, and multiply complex numbers. So let's look at what happens when we multiply conjugates of a complex number. And what is a complex conjugate? So the complex conjugate of the number a plus bi is a minus bi. And the complex conjugate of a minus bi is a plus bi. So just notice that the term separating the real and the imaginary part is just negated. So the multiplication, when you multiply complex conjugates, you end up with a real number. So look, a plus bi times a minus bi, we're going to end up with a squared plus b squared. And then it's the same thing if we multiply a minus bi times a plus bi. Order doesn't matter when we multiply, right? So we're going to end up with the same thing. And the reason is, look, let's look at this first one. So if I were to multiply a times a, I'm going to get a squared. Now I'm going to multiply a times negative bi, which is going to be negative abi. Now if I multiply the inner terms, I'm going to have a positive a times bi. And now I have to multiply my last terms, which are going to be, it's always going to be negative, right? Because you're multiplying a positive times a negative with the conjugate. So it's going to be negative bi times bi, which is b squared I squared. And don't forget, I squared is equal to -1, right? So this is a squared. The negative abi and the positive a times b times I sum to 0. And then we're going to have minus b squared times -1. And a negative times a negative is a positive. So we end up with a squared plus b squared. And that's what we have right here. And there's no imaginary part, right? So look, example 3, let's multiply these conjugates. 2 plus 5i times 2 minus 5i. So we're going to multiply first terms. 2 times 2 is 4. 2 times negative 5i is negative 10i. Multiply your inner terms. 5i times 2 is a positive 10i. So there you go. Your middle terms are going to disappear. And then the last terms, we're going to get negative 5 times 5 is 25 times I squared. So we have 4, middle terms sum to 0, minus 25 times -1, because I squared is equal to -1. And 4 minus 25 times -1 is really 4 plus 25. And there's my a squared plus b squared, right? Think of the a as the 2 and the bi, the b is the 5, right? So we get 2 squared is 4, b squared or 5 squared is 25. And we could simplify that. We could add a squared plus b squared, right? 4 plus 25 is equal to 29. And we see we don't end up with a complex number, right? The multiplication of complex conjugates gives a real number. And the real number in our case for this one is 29. So I think that's important that when you recognize multiplication of conjugates, technically you don't really have to multiply it out and combine like terms. You know it's going to be equal to a squared plus b squared. So now let's look at complex number division. So the goal of complex number division is to obtain a real number in the denominator. In order to do that, we multiply the numerator and denominator of a complex number quotient, like a fraction that we have here, by the conjugate of the denominator to obtain this real number. It's almost similar to rationalizing the denominator. So remember when we had a square root in the denominator and we didn't want to write it like that because it's not proper to have that irrational number in the denominator. So we multiplied the numerator and the denominator by either the single radical that was in the fraction or the conjugate. We're going to do the same thing here, except we're speaking of complex numbers. So we don't want to leave a complex number in the denominator. So what we're going to do is we're going to multiply the numerator and the denominator by the conjugate of the denominator. So look, if I want to divide in A 5 plus 4i by 4 minus I, I'm going to multiply the numerator by the conjugate of the denominator. So the conjugate of 4 minus I is going to be 4 plus I, and then multiply the denominator by the same thing. Whatever you multiply by the numerator, you have to multiply by the denominator to keep this thing equivalent. Now look what's going to happen. We're going to end up with a real number in the denominator, right? Because we're multiplying conjugates. So let's multiply out. In the numerator, I'm going to have 5 plus 4I times 4 plus I. And then in the denominator, I'm going to have 4 minus I times 4 plus I. So in the numerator, I'm going to have 5 times 4, which is 20. Then 5 times I is a positive 5I. Multiply my inner terms, 4I times 4, which is going to be 16I. And then I'm going to have a 4I times I, which is going to be a positive 4I squared. And then in the denominator, I really don't need to multiply out that conjugate, right? Because I already know when I multiply conjugates, I'm just going to end up with a squared plus b squared, like I showed you in example 3. So look, think of a plus bi times a minus bi, right? That's multiplying conjugates. Where in this case, think of a is equal to 4, right? A is the 4. And then the b in the bi, right? There's nothing in front of the I, right? So it's a 1. So a is 4, b is 1. So we're going to get 4 squared plus 1 squared. And 4 squared is 16, and 1 squared is 1. So 16 plus 1 is 17. So my denominator is going to be 17. And let me write that out. So a is 4, so we're going to get 4 squared plus b squared, which is 1 squared. And that's where I'm getting the 17. So let's simplify this. In the numerator, I'm going to have 20 plus 21i, right? 5i plus 16i. And then plus 4, but remember, I squared is equal to negative 1. So I'm going to have positive 4 times negative 1 is negative 4. And this is going to be over 17. 20 combined with a negative 4 is 16. So we're going to have 16 plus 21i over 17. Now we want to write this in standard form. So it says to divide and express the result in standard form. And remember, standard form is a plus bi. So in order to write 16 plus 21i over 17 in standard form, divide each expression in the numerator by 17. So I'm going to have 16 over 17 plus 21i over 17. So now I'm in standard form. The real part, the a is 16 over 17 plus the b, which is 21 over 17 times I. So another way you could think about writing this is 16 over 17 plus 21 over 17 I. So that's how we would write our answer in standard form. Just divide out by the denominator. And let's do one more. So let's take 2 minus 3i divided by 5 plus I, and let's express the result in standard form. So in order to get rid of a complex number in the denominator, we multiply by the conjugate. So I'm going to multiply the numerator and denominator by the conjugate of 5 plus I. The conjugate's going to be 5 minus I. So I'm going to multiply the numerator and the denominator by 5 minus I. So we're going to have 2 minus 3I times 5 minus I. And we're going to divide that by 5 plus I times 5 minus I. So let's distribute in the numerator. So we're going to have 2 times 5 is 10. 2 times negative I is negative 2I. Negative 3I times 5 is negative 15I. And negative 3I times negative I is going to be positive 3I squared. And now in the denominator, since I'm multiplying complex conjugates, I know I'm going to get a squared plus b squared, where a is 5. So I'm going to have 5 squared plus b squared. And again, b is the coefficient. It's the real number on the I term, which is 1. So 5 squared plus 1 squared. And now let's simplify the numerator. And don't forget, I squared is equal to negative 1. So I'm going to have 10. The negative 2I and the negative 15I, that's going to combine to a negative 17I. And now I have that positive 3 times negative 1, which is going to be negative 3. And this is going to be over 5 squared plus 1, which is 25 plus 1, which is 26. 10 minus 3 in the numerator is going to be 7. So we have 7 minus 17I over 26. And if I want to write that in standard form, I'm going to divide both parts of the numerator by 26. So I'm going to get 7 over 26 minus 17 over 26 times I. And that would be my complex number in standard form. So that's how we divide complex numbers. Make sure you multiply the numerator and the denominator by the conjugate. So next we're going to look at the principal square root of a negative number. So for any positive real number b, the principal square root of the negative number b is defined by the square root of negative b, but we could write that as I times the square root of b. And the reason is let's go back to that first slide. The definition of the imaginary unit I is the square root of negative 1, right? I is equal to the square root of negative 1. That's the imaginary unit. So let's write this up here. I equals the square root of negative 1. So for example, in example 5, look at A, the square root of negative 9. We can factor out a negative 1, right, from negative 9, because remember, we can't take the square root of negative 9. If you were to go to plug that in the calculator, square root of negative 9, you're going to get an error, right, because we can't take the square root of a negative number. But what we can do is we could factor out an I by factoring out a square root of a negative 1. So look, I can rewrite the square root of negative 9 as the square root of negative 1 times the square root of 9, right? Because negative 1 times 9 is negative 9. Just like we were factoring and simplifying square roots in chapter P. And we know the square root of negative 1 is I, and the square root of 9 is 3. Right? So this is I times 3. But we would write it in standard form, which is going to be 3 times I. So let's look at B. We're going to factor out a square root of -1 again, right? So we're going to end up with the square root of -1 times the square root of 49. Square root of -1 is I. Square root of 49 is 7. So we're going to get I times 7, or 7I. What about C, the square root of -80? 80 is not a perfect square, but let's use our radical rules like we were using in chapter P, right? Let's factor the 80. What's the largest perfect square that's a factor of 80? And we still have to factor out the -1, right? So I'm going to get the square root of -1 times the square root of, how we're going to factor 80? Well, we're going to do 16 times 5, right? Because 16 is a perfect square, and 16 times 5 is 80. So the square root of 16 times the square root of 5. Square root of -1 is I, square root of 16 is 4, and we can't simplify the square root of 5. So this is going to be, instead of I times 4, we're going to write 4 times I times radical 5. And let's look at part D. So for part D, again, square root of -75, we're going to factor out a square root of -1. And 75 has factors of 25 and 3, right? And 25 is a perfect square. So we're going to write that as the square root of 25 times the square root of 3. And the square root of -1 is I. Square root of 25 is 5. So we're going to get I times 5 times the square root of 3. And this is going to be equal to 5 times I times the square root of 3. So that's how we simplify a principal square root of a negative number. We can also perform, our operations of addition, subtraction on square roots of negative numbers. We would just write them in terms of I. So look at example 6. So example 6 says, perform the indicated operations and write the result in standard form. So if I want to add, like in A, the square root of -27 plus the square root of -48, I can only add radicals if they're like, right? So I'm going to have to rewrite these two radicals in simplest form and see if they're going to be like. So I'm thinking, okay, 27, it's negative, so I'm going to factor out a -1. And then square root of 9 times square root of 3, right, is going to give me 27, and 9's a perfect square. And then for 48, I'm going to factor out the square root of -1. And then 16 times 3 is going to be the factorization that I'm going to use, because 16 is a perfect square, right? And 16 times 3 is 48. So square root of -1 times the square root of 9 times the square root of 3 is going to be 3i times the square root of 3, plus square root of -1 times square root of 16 is 4i, and then times radical 3. And now you could see that these are like radicals, right? So we could add them. So add the 3i and the 4i, which is going to give me 7i, and then times the square root of 3. So 7i radical 3. Now let's look at B. We're going to do the same thing. We have to factor the radicands, right? So let's factor out a negative square root of -1. And then 16 times 2 is 32, right? So I'm going to have the square root of 16. Let's rewrite that. So I'm going to have the square root of 16 times the square root of 2, and we have times the square root of x. Don't forget about the x under there. It's part of the product. And then plus, now from the -50x, let's factor out a square root of -1. The factors of 50 I'm going to use are 25 and 2, right? Because 25 is a perfect square. And then don't forget about the square root of x. So now let's simplify what we have on the left, right? Square root of -1 is I, square root of 16 is 4, right? So I'm going to get 4i and then times the square root of 2x. Plus square root of 25 is 5. So 5 times I, right? Because the square root of -1, and then times the square root of 2x. And now when I look at this in simplified form, I realize the radicals are like, and I could add them. So 4i plus 5i is going to be 9i, and then times the square root of 2 times x. And then let's do one more where instead of adding, we're going to be multiplying, right? Because in C, I have -2 plus the square root of -3 squared. So this is the same thing as -2 plus the square root of -3 times -2 plus the square root of -3, right? Anytime we square something, we're multiplying it by itself. So I'm just going to write it out that way, right? And now we have to distribute. So we're going to use our distributive property. So before I distribute, I just want to rewrite that square root of a negative number, right? The square root of -3. Let's write it in terms of I. So this is equivalent to -2 and then plus I times radical 3, right? So we did a bunch of them above. So all I'm doing is factoring out the square root of -1, which is I, and then we're still going to have times the square root of 3 because I don't have a perfect square, right? That's other than 1, that's a factor of 3. So we're just going to have to leave it as the square root of 3. Now multiply that by -2 plus I times the square root of 3. Now we can distribute. So I'm going to have -2 times -2, which is +4. Then I'm going to have a -2 times I radical 3, so minus 2I times radical 3. Now I'm going to multiply my inner terms, which is going to be, again, a -2 times I radical 3. And then plus my last terms, which is I radical 3 times I radical 3. So I times I is I squared. And then we're going to have radical 3 times radical 3. And radical 3 times radical 3 is 3. So that's going to be I squared times 3, or 3I squared. So we're going to have 4. We could combine the two middle terms, right? A -2I radical 3 and a -2I radical 3 is going to be -4I radical 3. And then plus 3I squared, but I squared is equal to -1, right? So that's really 3 times -1. So I have a 4 at the front plus a 3 times -1, which is a -3, right? So really 4 minus 3, which is 1, and then minus 4I radical 3. And that would be my answer in standard form. Because 1 is the real part, and then the 4 times I times radical 3 is going to be the imaginary part. So that wraps up complex numbers, section 1.4 on complex numbers. In the next lecture, we will start section 1.5 and we'll talk about quadratic equations.